Hello everyone, I'm Tom Landry. I'm a part of the ESGF Compute Working Team and Executive Committee, and I work at the CRIM, Computer Research Institute of Montreal. I am the coordinator of the geospatial expertise there. What I'll present to you is a view, my view, our view at CRIM from the ESGF Compute Challenge as an introductory topic. Then I'll present to you the Earth Observation Exploitation Platform open architecture on which we developed some experiments, including climate and other form of remote sensing info. I will speak to you about the problem statement. So what was the actual machine learning problem? What did we need to train a system to learn? What was the approach, so more the engineering aspect. I'll show you some results, pretty pictures, and then I'll conclude. So if we ask Google right now on the ESGF Compute Challenge, you will see a publication made on the OGC website, which is called the Earth System Grid Federation ESGF Compute Challenge. So if you remember at the last face-to-face meeting, we had a person from OGC and we presented the concept. So that what you would find there, I don't have time to go through all of this. What you would find there is the work we've done with the architecture we present using climate processes, climate data, and workflows. And one of the let's say the lowest priority objective of that was to talk about machine learning, so prepare the way for machine learning, which is the topic of my actual discussion. Yes, so going back on the architecture, so this is a platform architecture where machine learning was separately explored, but at the basis, it's been like I think a 3 years effort to develop a component to work with thematic exploitation platform on the side of the user and mission exploitation platform on the side of the data. So this is really a European Space Agency type of wording, but it's something that you can probably apply to your own portals, platform, and backend. So what's important, and I think what's a bit different and was referred to a couple of times, is really the move application to data paradigm. So it's something a bit different. To do that, we need applications, of course. We need packaging, we need workflows, and we need some special bits of engineering I will show to you. So what's you will see, I put a link of the engineering report. What was done lately in testbed 15 is everything on the application discovery sense. That was something sponsored by NASA, but we haven't been active in that. But CRIM has been active in since last year for machine learning tools and pipelines. And we use common workflow language. And what's also very different from what I see of users of WPS is that we use the latest version, which is a RESTful interface. So no more XML, and everybody is pleased. Yeah. So on the architecture, what you see is some kind of a two-tier architecture. One side is the ADES, Application Deployment and Execution Service, that resides near the data in the mission exploitation platform. So imagine the data right there, so the data provider. The EMS is on the side of the client, any type of heavy client or thin client or whatever, and receive requests from clients, receive requests for application development. So this is all the application marketplace scenario where you say, wow, this is a neat application. I will deploy it to that particular infrastructure where I have some accounts in. So this is really the two, and the interface shared between those two is the new WPS processing interface. So what was the challenge? So again, there was not a climate-related challenge for this, but please believe me when I say this is somewhat similar data. This is gridded data, high-resolution data, 32 bits, and so on. And for this, we worked a lot more on how to package, how to deploy, how it fits the architecture than on the science of it. So it's not a science project. So what we needed to do is to train a model to split water bodies, undifferentiated water bodies, into either lakes or rivers. So this is not like a water detection problem. The water is already detected. You need to use some information to say this part of the water body is a lake, the rest is a river. So how we did it, we trained the lake detector, and we said everything from the hydro that is not a lake must be a river. So that was one way to put it. The study region is I don't know, something like 300 square kilometers in somewhere in the near Ontario and Quebec border. We use very high resolution DEM, so elevation model at 1 meter resolution. And this is the region of study. So this is where you could imagine some whatever climate data and some phenomenon that you detect, but in that, what it is that we see is a topography of terrain, hydrography that was detected by some means that we're not aware of, and what we need to train is a machine learning that will say this is a lake and this is not a lake, this is a river. And this is a handcrafted feature. This is a nifty trick that we did to add some kind of a ponderation to everything that is close to a water body. And the further you go, the higher the value. So that's why here we're far from those two bodies. It's getting white. So this kind of give the attention to the machine learning system so it can better recognize. And we form a tensor, so basically a stack of three RGB images, three gridded layers, and this is the input that we provide to the training system, in this case a deep learning system. So here's the workflow that we proposed, and it's meant to be configuration based, so kind of like a workflow based solution. So everything we need to do is in the configuration file, and the major steps are these one. We need to look at the raw data, parse it, understand it, load it into memory, into tensor cubes or whatever the way you work, data chunks. We need to load the model, so we work with the pre-trained model. We can load it or can reload a checkpoint, a previously trained model. And then from there, we can either train a model and produce a neural net, or if we have the neural network, we can use it to infer features. In that case, this patch is a lake, could be any other thing you were looking for. So this gets packaged in a Docker image. So this is why it's an application in a sense. It's a standalone piece of code that can be downloaded and used in various environments. And the application, usable application, is when we put a neural net into it, a trained neural net. Now it's some intelligence into the application. So a simplified view on this, how do we operate with this? How do we work with this? So the first level, as I said, is a Docker image. So you pull it as a developer, you run it, and you have access to a library that helps you do what you need to do. So train and load model and so on. So it's PyTorch based. And it's an application you could use it into your favorite environment. What we do on top of this is we have common workflow language descriptor. So we add some more layers to it to say, this is what the type of input it gets, this is the type of output it gets, this is the type of process it does, this is the input, outputs, and so on. So this is like the WPS descriptor, but it's a bit more formalized. And from there, we want to go to deploy that, to say this application becomes a new application deployed somewhere, do WPS. So it gets deployed, and now we can use it with WPS 2.0. So a bit more on the model definition. We use the faster RCNN, so convolutional neural network, to train on tensor, on observed region, and the goal was to have bounding boxes on lakes. So some post-processing is still needed. The way the sponsor provided the data and asked the question, we still had to do some manual cutting afterwards. So one recommendation, one missing part of the machine learning, deep learning equation was to say we don't want to have bounding boxes on those characterized region, but we want to have a segmentation. So there is a technique called mask RCNN that can do both of them. You actually learn to segment and extract the part that you're interested to. So this is very powerful method. A bit on code. So as I said, this is all configuration based. So you can imagine it like a workflow. This is the intent a bit of the work to try to see if some part of the machine learning pipeline can be made into workflow. But for now, they're kind of application parameters. So first, we set up the data parser. These are basically custom custom parameters that say, well, here's the lake you were looking for. Is it the different threshold values and so on? So this is very custom to the problem we're looking for. Once it's done, we do the same, but we do the loader part. So we say, what is the transformation we want to do? We want to take all the data. We want to do tensors, and we want to fed that. We want to use the two tensor operation. Now the data, when it's loaded, is ready to be used by PyTorch, and so in the deep learning environment. And we can also say use 90% of the data to train and 10% to validate and so on. So this is also part of the workflow. And the last step of the workflow is to set up the model. We say now you have that data, you have that configuration. Use faster RCNN ResNet 50. So that particular architecture of the deep learning model, but we could use other ones, faster ones, better ones. But this is very, very standard. So you can imagine that as a standard architecture in any different type of deep learning system you have. And then this is where the fun starts, is that, and the challenge is to be able to run all of this into a command line with in a single line of code. So would mean that you get the application, you just do a Docker run, you provide it with a single line of code, and it runs and it do what it was trained to do. So this is what we have here, the process, I would say the application. Once you install it, it's called T-helper, training helper. You just point to the configuration file and to the output, and bam, you actually have an execution of the training that is done, and to WPS. So a few results, it does work. It's a difficult problem because it's a multi-resolution problem. We have very, very, very small lakes and very, very, very large lakes. So we have to train for that. What's difficult too is well, the sheer size of Canada. So scaling it and having enough data is difficult. And what we found is that we should have trained both a river detector and a lake detector to have more flexibility. But the point is that the technique worked in that architecture. So in conclusion, we as I said, for the specific problem we tried to do lake detection, well, it worked with a relatively small amount of data with very high precision. But we could have better performance with more data and different architectures. So what we found is that WPS is not necessarily friendly for experimentation, interactive experimentation, just like I would say data science. So it's really much interactive. You stop it, you get our intermediate result, and that's okay. So having access to real-time log, it's not perfect fit. On the open architecture, we do think it's a very good fit, both for Earth observation and climate. So we've tried it for machine learning applications. So just like the one I showed to you, which is a standalone full pipeline of machine learning. We've used it for Earth observation processes, mostly remote sensing, extraction, detection, and so on. But these also becomes machine learning application. More and more, and we've used it also with climate application, mostly with climate indices. So in the ESGF Compute Challenge, we've used different pre-deployed services. So some at NASA, the subsetter, and the data from Lawrence Livermore, and we've passed it to CRIM, subsetter, and so on. So we designed a few chains to try to integrate that. Very, very obviously is that as it is right now, our implementation of the I would say the part that process the application, the ADES, the application deployment, it's monolithic. So it gets the application, it spins it once, and that's it. So very, it's clear to us that we need to scale with Kubernetes. So you can have a single request that would spawn, I don't know, thousands of different regions, for instance. So this is ongoing work also. As I said, it should be applicable to climate client and climate data, and if not, it needs to be. And I will get your attention on the pilot project of OGC and the European Space Agency that will spawn from January to June. That is supposed to mature some of this technology, and we hope to present both machine learning climate and Earth observation applications. So there it is.